Okay, so today I will continue with week 4 on ML course. I finished on regularization and logistic regression. So yeah, I finished like two of the article today, yesterday. And yeah, well, I will try to finish today these 3 articles, and yeah, well, maybe that's all for today. And also I want to cover Khan Academy, statistics course on Khan Academy. So yeah, where is my plan for today? Yeah, here it is. So 2 pomodors for ML course, then course on Khan Academy, and then again ML course. So I hope I will cover theory today and go dive to these topics for assignments. Maybe like in Tuesday or something. And what else I wanted to do? Yeah, well, maybe tomorrow I will not stream because of my plan, but because of my schedule or something. And yeah, but I will try to cover like these videos, like theory videos. I will not watch this practical part about Alice competition, because it will be on I think on next week, or no, it will be on like in the one of the weeks, on week 6. So I will not like spoil for myself joy of beating baseline by myself, but I could actually. And yeah, business case, yeah, maybe I will watch it on stream. Yeah, what it is actually. It's YouTube video. Well, I'm not sure that I want to watch it here, so maybe maybe I will not. Okay, so let's dive into the theory again. Linear classification and regression. An illustrative example of logistic regression regularization. In the first article, we demonstrated how polynomial features allow linear models to build non-linear separating surfaces. Let's now show this visually. Let's see how regularization affects the quality of classification on a dataset. On microchip testing from Andrew Enges. course on machine learning. We will use logistic regression with polynomial features and vary the regularization parameter C. First, we will see how regularization affects the separating border to the classifier and intuitively recognize under and overfitting. Then we will choose the regularization parameter to be numerically close to the optimal value via cross-validation and grid search. Oh, okay. So what was then? So let's import some libraries like NumPy, Pandas, sklearn preprocessing. I didn't meet it before, so I haven't met this before. This like library before, so this function model or something. So yeah, I think yeah, we met only like grid search CV, of course. We search like different. We try to choose the best parameters for the for our task. Cross-val score. Yeah, well, yeah, 3 of them I don't know. So matplotlib, yeah, we match. This one just for graphics, just for like this one for graphics and this one also for visualization. Okay, yeah. That's covered. Let's load the data using read as CSV from the pandas library. This is that set on 118 microchips objects. There are results for true test of quality control, two numerical variables, and whether the microchip went into production. Variables are already centered, meaning that the column values have had their own mean values subtracted. Thus, the average microchip corresponds to a zero value in the test result. Okay, so below the data, test. Okay, we have two tests. I think okay, so I think session is not working. Just reload it one more time. Yeah, well, so this here I can see that session like is starting, but it's not started yet. So haven't started yet. So let's try it. Okay, so we imported it again, and yeah, so 180 entries from 0 to okay, and we have three columns. Two of them are tests, two numerical variables, and information whether the mixture went into production. Variables already centered. Okay, so I think this one is I don't know, boolean. Must be boolean, so it must be 0 or 1. Okay, so I'm not sure what is this number, what this number means. So okay, so this kind of like maybe response, some electrical response or something. Let's like pretend that that's true. I'm not sure what it is. So we tested every chip with these parameters. We tested 2 chips, got some results. I guess by now that there were like different tests, so like the numbers are really different, but in every count they're kind of close between each other. So yeah, okay, so okay. Now we should save the training set and the target class labels in separate numpy arrays. Okay, so let's try to check how is this work. Okay, so how is ilog works? So can I? Mhm. Well, I forgot how ilog works in pandas. I know that he chooses some kind of like part of the data set, but data frame, but I don't actually remember syntaxes, so maybe it should be better to check it one more time. So integer allocation based on. So yeah, it's just for numbers as far as I know. It's for numbers. Well, it's for numerical columns, etc. So yeah, like he doesn't care about names of the like test above columns or rows. He just like go into the numbers. So yeah, so 0 must get us first line. So first one must be like strings. So we got every strings that we need, and here we got yeah, here we got from first to the third rows, and then from the here we got from the second to the third, fourth strings. Zero. Mhm. Okay, row selection and column selection, yeah. Integer of row, size of rows. So yeah, if we put here, so yeah, like 2 dots means that we got only like every strings. Like I can put like here 1, 2, 3, so it will be like from the second string to the third string. But and here we got columns. So I think that means that we got from the first one to the second one, I guess. And here we also got every strings, and we got like, yeah, I think we don't like, okay, so I think, yeah, so in range here we don't count like last number here, so we got from first to the second, and this one is actually third because we start counting with 0. Yeah, but if we put like just 2 here, so it will mean like we will get the third columns, which is like this one. Okay, so and we have matrix of like samples and vector of answers, our target vector. Okay. As an intermediate step, we can plot the data. Orange points correspond to defective chips, blue to normal ones. Okay, so okay, let's define a function to display the separating curve of the classifier. So this is the task of classification, but classification problem. So yeah, we need to curve. Okay. So here we build. Oh, okay, so we took what we took the first column, took minimal value from this. Same for maximum value. Here minimum value and maximum value, and then okay, so we have like we got like for each axis we got like a minimum, minimal, and maximum value, and grid and parent, and we create grid like from maximum to minimum value. Okay, and here yeah, we did it in this part of code, and every point from we put in some colors. So after that we Okay, and so let's try to understand what is happening here. What is happening here? Self predict qualify. I don't know. Generate polynomial and interaction features. Generate a new feature matrix consisting of all polynomial combination of the feature with degree less than or equal to the specified degree. For example, if an input sample is two-dimensional and the form so yeah, okay, let's see. Maybe it's explained further. We define the following polynomial feature of degree d for two examples, for two variables x1 and x2. So okay, so I think I got it. So we get like every like combination of powers of like these expressions where e and I and g is are like powers of the variables. So like x in degree 1, x1 in degree 1, x2 in every other degrees. Yes, so okay. But what? Okay, drawing a Pythagorean triangle would show how many of these features there will be for d 4, 5, and so on. The number of such features is exponentially large, and it can be costly to build polynomial features of large degree for 100 variables. More importantly, it's not needed. We'll use a scalar implementation of logistic regression. So we create an object that will add polynomial features up to degree 7. Let's train a logistic regression with regularization parameter d. Slot boundary. We could now try increasing c with 1 and doing so doing this, we weaken regularization, and the solution can now have greater values in absolute value of model weight than previously. Now the accuracy of the classifier on the training set improves to 0 point say why don't we see even more? Not exactly not strong enough and we see overfitting. Note that VC is equal to 1 and a small boundary. The share of correct answer on the training set is not much lower than here, but one can easily imagine how our second model will work much better on new data. As a result, let's write the function that is optimized in logistic regression with the form where L is the logistic loss function summed over the entire dataset. C is the reverse acquisition coefficient, the very same C from S-calculum, implementation of logistic regression. The larger the parameter C, the more complex the relation in the data that the model can recover. Intuitively, C corresponds to the complexity of the model capacity. If regression is too strong, the values are small. Solution to the problem of minimizing the logistic loss function is one where many of the weights are too small or zeroed. The model is also not sufficiently penalized for errors. Function the sum of. In this case, the model will underfit in our first case. On the contrary, realization. Okay, well, yeah, I will like go to the break. So yeah, I will finish it after the break. Yeah. Meanwhile, I will like open another one, last previous topic. So I will check the check my theory. Check the theory. This topic was about linear classification. So, pyramid. let's proceed. So C parameter C is response to the complexity of the model. Okay. Yes. So okay. On the contrary, representation to weak vector V with high absolute value. The component can become solution optimization problem. In this case, has a greater contribution. As it does with the way that is to say cannot be determined by solving the conjectural logistic regression. We have seen similar situation before. Decision tree cannot learn for depth limit used during the training process. Therefore, C is a model hyperparameter that is tuned on cross validation, so is the max depth in the tree. Okay, so regularization parameter tuning. This example, let's identify the optimal value of the regularization parameter C. This cannot be done using logistic regression CV, agreed search of errors followed by cross validation. This can be done. Yeah. I thought this cannot be done. I understand. The class is designed specifically for logistic regression, effective algorithm with well-known search parameters. For an arbitrary model, use grid search CV, randomized search CV, or special algorithms for hyperparameters. Hyperparameter optimization, such as the one implemented here. Opt. So to see how the quality of the model varies with the hyperparameter, can plot the graph. So this is like, I think this is the accuracy of the model. So we got like 0.8 or something. So finally select the area with the best value C. Because that the curve are called rotation curves. Previously we built them manually, but sklearn has special methods to construct this we will use going forward. Yeah, here we have the peak. So okay. Yes, so I think today, okay, let's try to like to go through the theory again, and maybe I will like try to revise it later. So Okay, the linear classification regression where logistic regression is very. Yeah, article outline. Okay, analyzing of IMDb movie reviews. Now for a little practice. We want to solve the problem of binary classification of IMDb movie reviews. Have a training set with marked reviews. 1250 review and 12,500 reviews marked as good and other bad. Here it's not easy to get started with machine learning right away because we don't have the matrix X. We need to prepare it. We will use a simple approach, back of words model. Pages of the review will be represented by indicators of the presence of each word from the whole corpus in this review. Whole corpus is the set of all user reviews. The idea is illustrated by pictures. A feature of the review will be represented from the corpus in the review. How you get ends. Tokenizer, build vocabulary over all document. Pass, and code. Yeah, didn't open Kaggle version. So import all libraries that we need. To get started, we automatically download the dataset from here and unarchive it along with the rest of dataset in the data folder. Let us briefly describe here. There are 20.5k of good and bad reviews in the test and trainings. Much more reviews. This is dataset for binary sentiment classification containing dataset. We provide this is do I need I don't want. So okay, here what we are doing, we import library request which we need for to do like URL request. I mean request with sites or something, so we can download something, like click something with this. Okay, so we define URL, so I think yeah, so okay. So exact path, input path. Response request help. Not sure why what this library is, but I think it's for the for the file, so we can open it, here read and write archive files. Yeah, something like that. Module makes it possible to read and write archives, including those use a zip file module to read or write zip files or the higher level functions in Patil. Okay. So here we open it. Okay. Okay, so I think something went wrong with files, with connection maybe. So yeah, let's go to the statistic version of this topic. One is not working. Okay, so there they download it, then change if you have it in notification. So yeah, well, I think I can download it by myself and use this function. This part of code. Okay. Now documentation documents training data. Okay, here are a few examples of the reviews. Words can describe how bad this movie is. I can find by you have to see it for yourself to get and grip how to read it. And now that I recommend you to so many text. Okay. First, we will create a dictionary of all the words using count vectorizer. Okay. If we look at examples of words, let's call them tokens. You can see that we have omitted many of the important steps in text processing. Automatic text processing can itself be a completely separate series of articles. Secondly, we are encoding the sentence from the training set text with the indexes of incoming words. We will use the sparse format. Let's see how our transformation worked. This move is terrible, but it has some good. Okay. Third, we will apply same operation to the test set. The next step is to train logistic. Okay, so we transform like words into the like some kind of code, and then we like use it as matrix for logistic regression. Okay, let's look at accuracy on both the training and the test sets. The coefficients of the model can be beautifully played. Visualize negative, interesting. To make our model better, we can optimize the regularization coefficient with logistic regression. We will use a sklearn pipeline because count vectorizer only be applied to the training data so as to not peek into the test set and not count word frequency there. In this case, pipeline determines the correct sequence of actions. Apply count advisor, then train logistic regression. Okay. Let's print the best C and as we score using the hyperparameter. For the validation set, now let's do the same with random forest. We see that with logistic regression, we achieve better accuracy with less effort. XOR problem. Let's now consider an example where linear models are worse. Linear classification methods still define a very simple separating surface, a hyperplane. The most famous toy example of where a class cannot be divided by a hyperplane line with no errors is the XOR problem. XOR is exclusive OR, a Boolean function with the following truth table. So 0 or 0 is 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. So I guess this kind of like opposite of O. So if we got O0, O0, we got 0. Ah, no, never mind. It should be 1. Is the name given to a simple binary classification problem in which the classes are pretended as and diagonally extended. So intersection point class. That was some random data set again, and then we use this boolean function them. So we use it for the for every rows in this matrix, and plot scatter plot. Obviously one cannot draw a single straight line to separate one class from another without errors. Therefore, logistic regression performs poorly with this task. Okay. But if one were to give polynomial features as an input, then the problem is solved. Yeah, kinda. Here, logistic regression has still produced a happy plan, but in a 6-dimensional feature space. When we project to the original feature space, x1, x2 boundary is non-linear. Okay. In practice, polynomial feature to help, but it's computationally inefficient to build them explicitly. SVM with the kernel trick works much better. In this approach, only what is this? Not sure. Support vector machine. Supervised. So yeah, we got classification. Yeah, it's supervised machine learning methods. Yeah, so we already have. We met this. Well, not so like didn't really understand. So the first example was like Boolean binary classification problem, and it was like easy. It was good. Like logistic regression was good here, linear regression, whatever. But in this problem, I don't know. Not so sure. What was the problem? Like, was it like not linear problem or what? Hard to say. Hard to say how to classify this problem. Okay, so week 4. What was it? It was article 4. Four. I where that. So they gave us just 2 examples, and it wasn't like very sure, really sure. I wasn't really sure how to do it, to implement it like in real tasks. But okay. So, and we have like last topic here. So I will close everything while it's opening. Yeah. After that, I will go to the break. So like usual. Yeah, it should be the big break, but I will not like spend all the time on this, so on all 50 minutes, so I will be back earlier than 50 minutes. So okay, so while it's loading, be right back. Okay, let's continue. Well, while I have some time, I will find on Discord because I closed it. Oh. Earn. So last run picks, yeah, I remember it. So okay, let's go into the one. So what it is? So campaign distributions with dot plots. Example problem.
At the Olympic Games, many events have several rounds of competition. One of these is the men's 100-meter backstroke. The upper dot plot shows the times in seconds of the top 8 finishers in the semifinal round at the 2012 Olympics. In the lower dot plot shows the times of the same 8 swimmers but in the final round. Which pieces of information can be gathered from these dot plots? In the semifinal round, we see that these are the 8 times of the 8 swimmers. We see 3 swimmers finished in exactly 53.5 seconds. One swimmer finished in 53.7 seconds right here, and one swimmer right over here finished in 52.7 seconds. So we can think about similar things for each of these dots. Now in the final round, one swimmer here went much faster. So this is in 52.2 seconds, while this swimmer right over here went slower. We don't know which dot he was up here, but regardless of which dot he was up here, this dot took more time than all of these dots. So his time definitely got worse. And this is at 53.678 seconds, 53.8 seconds. So let's look at the statements and see which of these apply. The swimmers had faster times on average in the finals. Is this true? Faster times on average in the finals. So if we look at the finals right over here, we could take each of these times, add them up, and then divide by 8 the number of times we have. But let's see if we can get an intuition for where this is. Because we're really just comparing in the finals. Is this true? Faster times on average in the finals. So if we look at the finals right over here, we could take each of these times, add them up, and then divide by 8 the number of times we have. But let's see if we can get an intuition for where this is, because we're really just comparing. We're comparing these two plots, or these two distributions, we could say. And so let's see, if all the data was these 3 points and these 3 points, we could intuit that the mean would be right around there. It would be around 53.2 or 53.3 seconds, right around there. And then we have this point and this point. If you just found the mean of that point and that point, so halfway between that point and that point would get you right around there. So the mean of those 2 points would bring down the mean a little bit. So maybe, and once again, I'm not figuring out the exact number, but maybe it would be around 53.2, 53.1, or 53.2 seconds. So that's my my intuition for the mean of the final round. And now let's think about the mean of the semifinal round. So let's just look at these bottom 5 dots. If you find their mean, you can intuit would be maybe right around someplace around here, pretty close to around 53.3 seconds. And then you have all these other ones that are at 53.5 and 53.3, which will bring the mean even higher. So I think it's fair to say that the mean in the final round at the time is less than the mean up here. And you could calculate it yourself, but I'm just trying to look at the distributions and get an intuition here. And at least in this case, it looks pretty clear that the swimmers had a faster times on average in the finals. It took them less time. One of the swimmers was disqualified from the finals. Well, that's not true. We have 8 swimmers in the semifinal round, and we have 8 swimmers in the final round, so that one's not true. The times in the finals vary noticeably more than the times in the semifinals.
Times in the finals where I'm.
That does look to be true. We see in the semifinals a lot of the times were clumped up right around here at 53.3 seconds and 53.5 seconds. The high time isn't as high as this time. The low time isn't as low there. So the final round is definitely they vary noticeably more. Individually, the swimmers all swam faster in the finals than they did in the semifinals.
From past in the
Well, that's not true. Well, whoever this was, they were one of these data points up here. This data point took more time than all of these data points. So this represents someone who took more time in the finals than they did in the semifinals. And we got it right. What I want to do in this video is look at some examples of data represented in different ways and think about which representation is the best or can help us answer different questions. So we see this first example. A statistician recorded the length of each of Pixar's first 14 films. The statistician made a dot plot. Each dot is a film, a histogram, and a box plot to display the running time data. Which display could be used to find the median? All right, so let's look at these displays. So over here we see the 14. This is the dot plot. We have a dot for each of the 14 films. So one film had a running time of 81 minutes. We see that there. One film had a running time of 92. One had a running time of 93. We see one had a running time of 95. We see two had running times of 96 minutes, and so on and so forth. So I claim that I could use this to figure out the median because I could make a list of all of the running times of the films. I could order them, and then I could find the middle value. I could literally make a list. I could write down 81, and then write down 92, then write down 93, then write down 95, then I could write down 96 twice, and then I could write down 98, then I could write down 100. I think you see where this is going. I could write out the entire list, and then I could find the middle value. So the dot plot I could definitely use to find the median. Now what about the histogram? This is the histogram right over here. And the key here is for median. To figure out a median, I just need to figure out a list of numbers. I need to figure out a list of numbers. So here, I don't know. They say I have one film that's between 80 and 85, but I don't know its exact running time. Its running time might have been 81 minutes. Its running time might have been 84 minutes. So I don't know here, and so I can't really make a list of the running times of the films and find the middle value. So I don't think I'm going to be able to do it using the histogram. Now with the box plot right over here, so I'm not going to click histogram. With the box plot over here, I might not be able to make a list of all the values, but the box plot explicitly tells us what the median is. This middle line in the middle of the box that tells us the median is, what is this? This median is, if this is 100, this is 99. So this is 95, 96, 97, 98, 99. It explicitly tells us the median is 99. This is actually the easiest for calculating the median. So I'll go with the box plot. So the histogram is of no use to me if I want to calculate the median. Let's do a couple more of these. Nam owns a used car lot. He checked the odometers of the cars and recorded how far they had driven. He then created both a histogram and a box plot to display the same data. Both diagrams are shown below. Which display can be used to find how many vehicles had driven more than 200,000 kilometers? So how many vehicles had driven more than 200,000 kilometers? So it looks like here in this histogram, I have 3 vehicles that are between 200 and 250, and then I have 2 vehicles that are between 250 and 300. So it looks pretty clear that I have 5 vehicles, 3 that had mileage between 200,000 and 250,000, and then I had 2 that had mileage between 250,000 and 300,000. So I'm able to answer the question. 5 vehicles had a mileage more than 200,000. And so I would say that the histogram is pretty useful. But let's verify that the box plot isn't so useful. So I want to know how many vehicles had a mileage more than 200,000. Well, I know that if I have a mileage more than 200,000, I'm going to be in the fourth quartile, but I don't know how many values I have sitting there in the fourth quartile just looking at this data over here. So that's not going to be useful for answering that question. Let's look at the second question. Which display can be used to find the median distance? Which display can be used to find the median distance was approximately 140,000 kilometers? Well, to calculate the median, you essentially want to be able to list all of the numbers and then find the middle number. And over here, I can't list all of the numbers. I know that there's 3 values that are between 0 and 50,000 kilometers, but I don't know what they are. It could be 10,000, 10,000, 10,000. It could be 10,000, 15,000, and 40,000. I don't know what they are. So if I can't list all of these things and put them in order, I really am going to have trouble finding the middle value. The middle value is going to be in this range right around here, but I don't know exactly what it's going to be. The histogram is not useful because it's throwing all the values into these buckets. While on the box plot, it directly tells me the median value. This line right over here, the middle of the box, this tells us the median value. We see that the median value here, this is 140,000 kilometers, right? This is 100, 110, 120, 130, 140,000 kilometers is the median mileage for the cars. And so the box plot clearly gives us that data.
Okay, with histogram we can say what is median. With box plot we can say like exactly how many numbers we have, like in each like percentile or something, or quantile. So yeah.
What we're going to do in this video is start to compare distributions. So for example, here we have 2 distributions that show the various temperatures different cities get during the month of January. This is the distribution for Portland. For example, they get 8 days between 1 and 4 degrees Celsius. They get 12 days between 4 and 7 degrees Celsius, so forth and so on. And then this is the distribution for Minneapolis. Now, when we make these comparisons, what we're going to focus on is the center of the distributions to compare that, and also the spread. Sometimes people will talk about the variability of the distributions. And so these are the things that we're going to compare. And making the comparison, we're actually just going to try to eyeball it. We're not going to try to pick a measure of central tendency, say the mean or the median, and then calculate precisely what those numbers are for these. We might want to do those if they're close, but if we can eyeball it, that would be even better. Similar for the spread and variability. In either of these cases, there are multiple measures in our statistical toolkit. Center, mean, median is valuable for the center. For spread variability, the range, the interquartile range, the mean absolute deviation, the standard deviation, these are all measures. But sometimes you can just kind of gauge it by looking. So in this first comparison, which distribution has a higher center, or are they comparable? Well, if you look at the distribution for Portland, the center of this distribution, let's say if we were to just think about the mean, although I think the mean and the median would be reasonably close right over here, it seems like it would be around it would be around 7 or maybe a little bit lower than 7. So it would be kind of in that range, maybe between 5 and 7 would be our central tendency, would be either our mean or our median. While for Minneapolis, it looks like our center is much closer to maybe -2 or -3 degrees Celsius. So here, even though we don't know precisely what the mean or the median is of each of these distributions, you can say that Portland distribution has a higher center, however you want to measure it, either mean or median. Now, what about the spread or variability? Well, if you just superficially thought about range, you see here that there's nothing below 1 degree Celsius and nothing above 13. So you have about a 13-degree range at most right over here. In fact, what might be contributing to this first column might be a bunch of things at 3 degrees or even 3.9 degrees. And similarly, what's contributing to this last column might be a bunch of things at 10.1 degrees. But at most, you have a 12-degree range right over here. While over here, it looks like you have it looks like it's approaching a 27-degree range. So based on that, and even if you just eyeball it, we're using the same scales for our horizontal axes here, the temperature axes, and this is just a much wider distribution than what you see over here. And so you would say that the Minneapolis distribution has more spread or higher spread or more variability. So higher spread right over here. Let's do another example, and we'll use a different representation for the data here. So we're told at the Olympic Games, many events have several rounds of competition. One of these events is the men's 100-meter backstroke. The upper dot plot shows the times in seconds of the top 8 finishers in the final round of the 2012 Olympics. So that's in green right over here, the final round. The lower dot plot shows the times of the same 8 swimmers, but in the semifinal round. So given these distributions, which one has a higher center? Well, once again, I mean, and here you can actually, it's a little bit easier to eyeball even what the median might be. The mean, I would probably have to do a little bit more mathematics. But let's say the median, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8 data points. So the median is going to sit between the lower 4 and the upper 4. So the central tendency right over here is, for the final round, looks like it's around 57.1 seconds, while especially if we think about the median, while the central tendency for the semifinal round, let's see, 1, 2, 3, 4, 5, 6, 7, 8, looks like it is right about there. So this is about more than 57.3 seconds. So the semifinal round seems to have a higher central tendency, which is a little bit counterintuitive. You would expect the finalists to be running faster on average than the semifinalists, but that's not what this data is showing. So the semifinal round has higher center, higher.
So go backward. Wait a minute. Okay, sorry. A small median time in the final round indicates the finalists were faster. Small median. Why is that so?
Center, and I just eyeballed the median, and I suspect that the mean would also be higher in this second distribution. And now what about variability? Well, once again, if you just looked at range, and these are both at the same scale, if you just visually look, the variability here, the range for the final round is...
Well, maybe I should go through it more precisely. So if the median is higher, then then it means that swimmers are faster or what? Okay. I think it's quite like useful to understand more about median or something. No.
Larger for the semifinal round. Let's see, 1, 2, 3, 4 buttons. Counterintuitive what this data is showing.
So I wanted to find these nodes again. Here is this node. So got it backward. The small median time in the final round indicates the finalists were faster. Yeah. Well, not so sure about it. Okay, so the small median time is in final round indicates the finalists were faster. Okay, for example, let's just create like, I don't know, seven numbers, like 1, 2, 4, 5, 6, 7. I mean, let it be like speeds of someone, I don't know, or time of like some of the races. And in another way, another it will be like 2, 3, 4, 5, 7, 8. Okay, so what we have here, median is in the first, like, let it be semi, let it be final. So here median is 4. Here median is 5. Okay. So here everyone was faster, but in median is also more. So okay, let's. So this rule is not like something like for every cases, but let's look at this one again. So what is median here? Median is here. So I don't know.
It's right about there. So this is about 57, more than 57.3 seconds. So the semifinal round seems to have a higher central tendency, which is a little bit counterintuitive. You would expect the finalists to be running faster on average than the semifinalists, but that's
It's not so clear. Okay. Well, I know that. Well, actually, the only thing that I didn't send them this one. So I was talking. Why are they in? Okay, so okay, I didn't want to do it, but let's like calculate mean average in final and 56. Okay, so let's open calculator. So 56 plus 6 plus 56.6. We calculate 6, 7, 8, 9. Yeah, we will calculate average for final. Multiply by 2 plus 57, 7, 7, 1, 57.2, 57.7, 57.7, and plus the last one, 57.9. And divided by 8. So 57.01. 75. Yeah, well, that's the average for the finalist. Let's calculate average for the semi-finalist. So it will be 56.7 plus 56. Yeah, I got it right. 57.2 plus 2 multiply 57.3 plus 57.4 7.6 and 8. Uh, 0.7, 7 and 8. Okay. Yeah, well, the average is high. I don't know. Okay.
It's not what this data is showing. It has a higher spread, and there's of course times where one distribution could have a higher range, but then it might have a lower standard deviation. For example, you could have data that's like, two data points that are really far apart, but then all of the other data just sits right. It's really, really closely packed. So for example, a distribution like this, and I'll draw the horizontal axis here just so you can imagine it as a distribution. A distribution like this might have a higher range but lower standard deviation than a distribution like this. Let me just I'm just drawing a very rough example. A distribution like this has a lower range, but actually might have a higher standard deviation. Might have a higher standard deviation than the one above it. In fact, I can make that even
Actually, really strange. They didn't give us a definition of standard deviation, but they already used it.
better. A distribution like this would have a lower range, but it would also have a higher standard deviation. So you can't just look at, it's not always the case that just by looking at one of these measures, the range or the standard deviation, you'll know for sure. But in cases like this, it's safe to say when you're looking at it by inspection that, look, this green, the final round data, does seem to have a higher range, higher variability, and so I'd feel pretty good at
The following accurate description of the following below. Yeah, well, I think I can skip. Rest. I don't want to go to the break. Okay, which of the following are accurate descriptions of the following below? The distribution has a peak at 4 years and year 4 and 4 years. No, it's not. It has a gap from 5 to 7 years. No, it's also not. None of the above. Nam owns a used car lot. He checked the odometer of the cars and recorded how far they had driven. He then created both a histogram and box plot to display this same data. Which display can be used to find how many vehicles had driven. Vehicle histogram and find the median box plot. Ben is considered that he is not reading enough. He decided to record how many pages he read each day for the month of April. And he makes a box plot of the data. Then he repeats the process for the month of June. His two plots are shown below. In there were 15 days and there were 15 days that Ben read between 25 and yeah, it's true, because here we have like half of the all days. In April we have actually 30 days. So here we have like half of it, and yeah, he read from 25 to, so it's true for April. And in June, Beck took a day off of reading. Well, yeah, well, it's true, because here we see like in June we have like at least one day outlier, so he read zero page, and here we have like every page. In every day we can see like he read at least 5, so the minimum one, yeah. So June. The history below shows the mass in kilograms of the offensive linemen of the University of Mount Union linemen and the University of Alabama football. Which pieces of information can be gathered from this histogram? The linemen who play for Mount Union have more mass of average. So okay, so yeah, we can calculate like from Alabama and mountain. So yeah, well, I think in Alabama have more mass than average. Yeah, I don't think so. The second all about have more mass. All of the yeah, it's also not true because, for example, these two guys have more weights than, for example, these two guys from yeah. So none of the above. Yeah. St. Louis, Missouri, and Washington D.C. have very similar latitudes. Latitude measures how far north or south a place is, which in turn affects the temperature. The box plot shows the daily high temperature in degrees that were recorded during July 2013 in each city. Okay, so last St. Louis, DC. Fill the blank. Fill in the blanks. The center of St. Louis distribution is less than, and variability in the St. Louis distribution is greater than. Okay. Is that what is? This one was. Okay. Next. Place.
An investment firm creates a graph showing the performance of a specific stock over 12 months. Over the course of the years, the price of the stock rising, falling, or staying the same. So over this axis right over here, the horizontal axis, they have month by month, and we move forward in time, July, August, September, October. And in this axis, the vertical axis, we have the price. So for example, in July, the price of this stock was a little over $10. Then in August, it moved up to, it looks like, around $11. And then we could keep going month by month. And this type of graph right over here is called a line graph because you have the data points for each month, and then we connected them with a line. And the reason why we connect them with a line is to really see if there's some kind of a trend here, to really show that you have something that's moving from one price to another. And so line graphs tend to be used when you have something that's changing over time. Now, with that out of the way, let's actually answer their question. Over the course of the year, is the price of the stock rising, falling, or staying the same? So on a month-to-month basis, you have, for example, from July to August, the price went up. Then from August to September, the price went down. Then it went up for 2 months. Then it went down for a month. Then it went up for a couple more months. Then it went really up from February to March, went all the way up to almost $17. Then it went down again, and then it kept going up again. But they're asking us not, did it go up every month? They're saying over the course of the year. Over the course of the year, is the price of the stock rising, falling, or staying the same? And if you go from July, which is where our data starts, right over here, our price was around $10. And even though there were a few months where it went down, the overall trend is that the price is going up. The overall trend is that the price is going up. And you can even see that. In July, it was $10, and then by June of the next year, it was approaching, I don't know, it looks like it's about almost a little over $16, maybe almost $17. So it actually had gone up a lot. They don't give us July of the next year, but the overall trend is definitely the upwards direction right over here. And you can see it just visually by looking at this line graph. Even though there's a few bumps that go down, the overall direction is upward.
Yeah, so idea was quite simple, I guess. We just like trying to understand the like main trend. So here we can see like his price or whatever percentage is decreasing, and here is increasing. So you can see it like I don't know. We can calculate like mean values and uh, like take two of them somewhere and plot a line between them, so we will see like if it's increasing or not.
Thrill Soda hired a marketing company to help them promote their brand against Yummy Cola. the company gathered the following data about consumers' preference of soda. So they have year by year, percentage of respondents who preferred Yummy Cola, percentage of respondents who preferred Thrill Cola, and these are people who had no preference. So in 2006, 80% liked Yummy, only 12% liked Thrill, and 8% didn't like either one or didn't have any preference. And so actually, just from here, you see that many more people liked Yummy Cola than Thrill Cola, actually every year over here. So Thrill Cola definitely has something, they have an uphill battle. But then they said the advertising company created the following two graphs to promote Thrill Soda. And so let's see what's happening over here. So let's think about whether this is misleading or not. So if we look at this graph over here, in 2006, sure enough, 80% liked Yummy Cola, then 2007, 76%, then it keeps going to then 77%, then 73%, then 73, then 68. So this is actually accurate data. It actually represents the data that's given right over here. I'll do the same. It actually represents this data very faithfully. Then right over here, if we look at this chart, percentage of people who prefer Thrill Soda. So over here in 2006, 12% preferred Thrill Soda, 2006, 12%, 2007, 19%, 2008, 19%, then we go up to 20, 21, and 25. So the graphs are actually accurate. They're not lying. These are actually the data points of the percentage who prefer Thrill Soda. Now what's misleading is if someone were to just look at these two graphs without actually looking at the scales over here, they'll see two things. They'll say, oh look, you see a declining trend, and that's what line graphs are good for seeing trends. They say, look, I see a declining trend in the percentage of people who prefer Yummy Cola, and I see this increasing trend in the percentage of people who prefer Thrill Cola. And that's true. You have a declining trend here, and you have an increasing trend here. But what's misleading here is the way that they've plotted the scales. These scales are not the same. So when you look at this, you say not only is there an increasing trend of people who prefer Thrill Soda, but the way they set up the scale, it looks like the trend is above. It looks like if the human brain is tempted to compare these, and they say, look, not only is this an upward trend, but it's above this trend right over here. Even in 2006, this data point looks higher than these data points right over here. But the reality is that it's only because the scale is distorted. And this is the oldest trick in the book when plotting line graphs. It all depends on the scale. So this just looks good because they used this scale that went from 0 to 30 as opposed to 0 to 100. The better thing to do, or the more genuine thing to do, or the more honest thing to do would have actually been to plot them on the same graph. Although if they did that, that wouldn't have painted a very good picture for Thrill Soda. So if we plotted on the same graph, Thrill Soda, let's try that out. So in 2006, 12, and actually this is even worse. You actually wouldn't even be able to plot Thrill Soda on this graph because they started this graph right over here at 50%. They didn't even start it at 0%. So you actually would not even be able to plot Thrill Soda on this graph. If you did, you would have to extend this graph all the way down. So you would have to extend this graph all the way down to, so this would have to be 40, this would be 30, this would be 20%, this would be 10%, and then or down all the way over here would be 0%, and then the Thrill Soda graph would be all the way down here. So it was like 12%, and it goes all the way up to like 25%. So the Thrill Soda, so it would have looked something like this. The graph would have looked something like this, which is nowhere near. If you plotted these on the same scale, on the same graph, then it would have still been pretty obvious that a lot more people, even though the trend is downward, a lot more people prefer Yummy Cola to Thrill Cola. So there's two very disingenuous things going on over here. One is the actual scale. For this amount of distance on this scale, they represent 10%. So whatever the gain is, it looks like it's a huge gain. And over here, that same amount, they're actually representing a larger amount. They're representing closer to 15 or 16%. And then the main thing is they started the scale here at 50%. So they're not showing how many people really prefer, how large 80% or even 70% really is. And over here, they start at 0 and they just have a larger scale. So it makes it look like out the gate, a lot of people prefer, or a comparable amount of people prefer Thrill, and that the trend is up. But the reality is still way more people prefer Yummy Cola. So this was a little bit, actually very, very not so honest way of representing the data. Or I guess you say they're misrepresenting the data.
So let's go to the unit test. I need to create histogram. So from 0 to 150 have only one unit. From 100 to 300 have two units. Or three. 1, 2. From 300 to 450 I have also 2 units, and only. What is the shape of a distribution balance? Usually skewed to the left, something symmetrical to the right. Well, it's skewed to the right. St. Louis, Missouri has very similar latitudes. Yeah, well, I think that's the same. So the daily high temperature varied more noticeably. So here variety is like it's 16 is in 16 degrees, and here is 12. So is it noticeably varied? I don't know. The daily high temperature in July were hotter on average in well, that's true. So I will check. Okay. In a recent experiment conducted by the Department of Energy, light bulbs were tested to measure how long they lasted. Each company submitted 20 light bulbs, which were turned on and left on until they burned out. Here was the result. All 20 super bright light bulbs burned out after exactly 1,500 hours. The first delightful bright light bulb burned out after this kind of, and one additional bulb burned out every 500 hours until they were all burned. Okay, so okay, I got it. So so we have like some few kinds of bulbs, and we will need to compare them. Okay, one of pretty bright light bulb burned out after just 16 hours. The other 19 bulbs lasted between okay, for super bright bulbs, the medium life will be equal the mean. Yes, because all of them are the same, while the median life will be okay, so I think here will be less, here will be high. Yeah. Okay. No. The median what? Okay, so here median will be in this range. Pretty bright. So median will be probably higher than the mean because this 16, yeah. And for the last one, median, yeah, we will this one. Okay, Bright bulbs out a consistent intervals 15 hours. Distribution shown below. These data points are arbitrary space. The mean and median can both be calculated by finding the exact between the median and mean are both yeah. I have one very low outlier. I'll bring down the mean, but it will not affect the median, but my match. Yeah, well, yeah, I didn't expect, yeah. So, yeah, it's fine. That below shows the number of hours of sleep that each of the 8 staff members at Ares Electronics got on Thanksgiving night. This data create a frequency table 6, 1, 2, 2, 7, 1, 2, 3, 4, 8, 2. The Baltimore Ravens won the American Football Championship in 2013. In the same season, the Kansas City Chiefs had the record of 2 wins and 14 losses. The dots below show the 40-yard dash times second of defensive backs on each team's roster. Defensive backs mainly depends against I had no idea what it means actually. I really don't know how to play it. Okay, so the center of guests in each hostel room. How many hostel rooms have 11 or fewer guests? So 3, 8, 16. Ken is trained to be a stylist. Below are the number of haircuts that gave during each of her 8 traineeships. The number of haircuts that she gave during using that created dot plot where each presents. So 15, 3. Yeah, statistician for a chain of department stores created the following stamp and leaf plot of pairs glass and each of the stores. What was the largest number of pairs of glass at annual one department store? 47. Which of the following distribution has a peak? Not true. Difference has a gap. Then I measure the mass of each pumpkin in his patch. The nearest tenth of a kilogram. He then created both histogram and box plot to display the same data. Each display can be used to find the maximum mass. So box plot, of course, and each display can be used to find that there were 25 pumpkins. It will be histogram. Okay, 1 minute left. Matrix table shows the number of goals Hank scored across season. How many seasons of lacrosse did Hank play? 1, 4, 6, 7. Okay. So yeah, I did it in time actually, which is great. So yes. So yeah, well, I will continue next time with this one. Yeah, well, it has lots of. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so it has still 12 lessons. Not sure that I will cover it in 12 days, but okay, so I will go to the break, and after that I will try to go through the theory again. Okay, so let's go back to the theory. So I finished, yeah, on this one. This unique classification regression, validation, and learning curves. So so as usual we import libraries. Now that we have an idea of model validation, cross validation, and regularization, it is a bigger question. What to do if the quality of the model is dissatisfying? Should we make the model more complicated or more simple? Should we add more features? Do we simply need more data for training? The answers to this question are not so obvious. In particular, sometimes a more complex model can lead to a deterioration in performance. Other time, adding new observation will not bring noticeable changes. In fact, the ability to make the right decision and choose the right method to improve the model distinguishes a good professional from a bad one. Yeah, well, in my opinion, you should try everything that was mentioned before. You can quality. Yeah, but okay, it's all on the experience and quality of data scientists again. We'll work our data on customer churn of telecom operator. Okay, we'll work our data. Okay, so yeah, I remember this. This data was in the first lesson, so we tried to analyze churn of the company. So we'll train logistic regression with stochastic gradient descent. Later in the course, we will have a separate top article on this topic. Okay. As a first step, we will construct validation curves, showing how the quality on training and test sets varies with regularization parameters. Okay, so so we took our data, we calculate mean, we calculate standard deviation, and then we plot a line for mean, and then we put some sort of I don't know, space for the standard deviation. So okay, and what we took alphas, what is alphas? The trend is quite visible and is very common. For simple models, training and validation errors are close and large. Okay, so what we have: training scores, validation scores. Okay, so Simple models training and validation errors are close and large. This suggests that the model underfitted, meaning it does not have a sufficient number of parameters. For highly sophisticated models, training and validation errors differ significantly. Can be explained by overfitting. When there are too many parameters, optimization is not strict enough. The algorithm can be distracted by the noise in the data and lose track on the overall trend. How much data is needed? The more data the model uses, the better. But how do we understand whether the new data will be helpful in any given situation? For example, is it rational to spend n for assessors double the data? Since the new data can be unavailable, it's reasonable to vary the training set and see how the quality of the solution depends on the amount of training data. This is how we get learning curves. The idea is simple. We display the error as a function of number of examples used in training. The parameters of the model are used in advance. Okay, so what we do in plot learning curves? Let's see what we got for the linear model. We will see the regularization coefficient be quite large. A typical solution for a small amount of data, errors between training and cross-validation sets are quite different, indicating overfitting. For that same model, but with a large amount of data, errors converge, indicating overfitting. If we add more data, error on the training set will not grow. On the other hand, the error on the test data will not be reduced. So we see that errors converged and the addition of new data will not help. Actually, this case is most interesting for business. It's possible that increases by 10 times, but without changing the complexity. This additional data may not help. Therefore, the strategy of set once and use 10 times. What happens if you reduce the regularization coefficient to 0.5? We see a good trend. The curves gradually converge and we move further to the right. Add more data to this model, we can improve quality of the validation set even more. Now what if we make the model even more complex by setting alpha? Overfitting is seen, decreasing on both the training and validations. Writing these curves can help understand which way to go and how to properly adjust the complexity of the model for new data. Conclusion on the error on the training set says nothing about the quality of the model by itself. Classification error shows how well the model fits the data. Validation curve is a graph showing the result of tests depending on the complexity. close to each other. Both arrows are large. It's 100 circles are each other. Showing is a graph showing the result. So, previous. Just can add the new data will necessary to change the complexity. If the colors have not data can improve the result. Okay. Okay, so I think I will go for a few minutes. So I will refresh myself a little bit, and after that I will try to go through the whole article one more time. So yeah, to get a little bit better with series. So it wasn't so easy for me, and I didn't understand. But let's try it. So be right back. Okay, so let's continue. Okay, let's go to the theory one more time, and also I want to 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 look properly more on code. So yeah, I checked. I missed some lines of it, so just run it or like read it, and didn't understand properly what was minted. So yeah, let's start with linear regression again, I think. Okay, this one I remember. So we have like some kind of features. We can like we can define our like target, or like describe our target variable with these features by like adding some weights to some of them. So some of them are more important, some of them are not, and we have like some kind of bias in the beginning, so we add it here. And if you want like to have more fancy formula, or which we can use more efficiently, we can add like some fictional parameters, fictional coordinate, and yeah, and got this formula for specific number, like for specific like representation of the target variable. And if we have like this is like each sample, one sample for each parameters, for each features, and we can like add like n of them, and we will have matrix X with it. Okay, so it's cool. After that, yeah, vector, yeah, my parameters. Okay, so yeah, my rank is independent because rank is full because we consider, I guess, so here, so our samples are like get independent between each other, so we don't have linear connection between different samples. But I guess we will have something close to this. Okay, so we have error and we have target here as well, so we can compute this for we can compute like each of the coordinates by using this formula. So we sum this for each element in vector of weights, and for each I think for each element we need to calculate for every column. Okay, so in order to get to satisfy in further like consideration, we will like set up some restrictions, so our solution will be the good one. So it's all on this error, so we set that expectation is 0, that variance is less than infinite and random, and they are uncorrelated. Okay, so by the way, I can spend some time to do at least one query relation in independence. So yeah, well, so I think this kind of okay. So the problem that I want to solve is, for example, what if we will have for example, if we have two uncorrelated variables random, so all two of them have like this property, so correlation between them is equal to 0, so covariance between them is equal to 0. So why is not from this not implies that they are not independent? So I think because we can construct some kind of example. Okay, correlation measure week 4 here crash for energy is equal to 0. Not implies that the IG is equal to 0. So those two variables might be associated in several other non-linear ways. Related relation couldn't distinguish from independence. As a very didactic, visual and non-realistic example, one can consider X, such as so X is equal to -1, 0, 1 with probabilities 1, 1, 1 third, 1 third, and third, and Y is equal to x quadrant. That they are not only associated, but one is a function of the others. Nonetheless, their correlation is 0, for their association is orthogonal. So, okay, they are not independent, but what is their correlation? Correlation of yes, so we have so well, let's try to calculate correlation. X is equal to covariance x y minus. So let's is equal to expectation of x minus expectation. So what it will be a correlation of the covariance, what will be like, and what will be standard deviation of variable x in this example. So let's try to calculate it. Will be okay, so expectation of x must be the sum -1 3 plus 0 plus 1 plus 1. So expectation of x is equal to 0. So is it true though? So yeah, let's keep it. So does it mean that the variance of this variable is equal to 0 or not? I guess no. Yeah, I guess yes. Well, expectation is equal to 0 for sure. Well, no, it's not true. So expectation of x in square. What is x in square? So I guess it will be 1 with probability 1/3, 2/3, and 0 with 1/3. So it will be 2/3. So yeah. Okay, so what will be? Okay, so well, I think yeah, I know how to calculate variance of y. So let's try to calculate covariance, because correlation will be 0 if and only if covariance will be equal to 0. So covariance x y is equal to expectation of, well, I will need to calculate expectation of y anyway, so I will do it. Okay, so well, I think I already calculated it. It will be equal, so expectation of x is equal to 0, expectation of y is equal to 2/3. So yeah, y is equal to x minus x multiplied by y minus third, something like that. So what it will be? Y is equal to 1 with probability 2/3 and 0 with probability 1/3, and then yeah, well, that I've calculated everything correctly. Yeah, well, I can calculate exactly why is they are not correlated. Yeah. Yeah, well, yeah, we see. Maybe not. Oh, yeah. That's what, that's, okay, so one more time. Well, I think I have pretty close to this ones, you know. Yeah, pretty close to this one. So, yeah, well, in my case, expectation of x is equal to 0, expectation of y is equal to 2/3. So yeah, well, but I couldn't like make it out from this one to this one today. So how it was look like? I needed to add y minus mu x, y minus mu y multiplied by, well, I needed to use like a formula for a joint expectation. Why? So let it be so. So okay. So okay, and so here we built. Okay, so yeah, I got so it's harder than I thought. So Okay, so if x is equal to 0, will be equal to 0 as well. So probability must be okay, so probability must be 1/3 because we want to choose as well as, so if we choose 0 we will get 0 for y anyway, but y for anyway, but we need to add here probability to choose x. Okay, so if we choose x as 0, so we will not get y as 1, so it will be 0. If we choose as x as 1, x is equal to 1, so we will not get y is equal to 0, and we will get y as 1 in 1/3 as well, and for minus 1 same. Okay, so what it will be? So let's try to now everything with x. If x is equal to 0, our sum will be 0 as well. So we can like remove this part. So we need to like iterate over x is equal to 1 and minus 1. So x is 1 minus 0 multiplied by y is equal to 0 minus 2/3 multiply by 0. Yeah, so it could be true. So plus 1 minus 0 multiplied by 1 minus 2/3 multiply by 1, it will be 1/3 plus minus 1 okay 0 0 if x, yeah, well yeah, so we will get only two non-zero elements in the sum. So what it will be minus 1 minus 0 1 minus 2/3 multiplied by 1/3, so it will be 1/3 1/9, and here we have minus 1/9. Yeah, it will be 0. Okay, so yeah, well, I didn't get this joint probability thing, so yeah, but now it's clear. So yeah, so I can check, independence. So proved. Task 1 week. Oh, okay, so yeah, I think I got it. Okay, so Okay, so yeah, I will like try to keep a count for the probability and statistic solutions. So every day. Okay, and where is the topic? Okay, here I got everything. Well, I still didn't see and haven't checked proof of this theorem, but I guess yeah, I still have it on my list, so I will like finish it maybe. I think so. I hope so. Okay, so estimator. Okay, so what it is? We don't know actually how our weights really look like. So in general, yeah, we like consider like so every maybe not is depend but not no. So okay, so how it really depends. So for every k depend only on samples from X, but not on. Okay, so okay. Let's edit one more question. So how on X. Not sure how it really depends. So okay, we somehow get like another weights coefficients. We like sum this with like with our targets parameters and like get estimation. Okay, at this point it's time to say that we don't plan to squeeze a whole statistics course into one article, so we try to provide the general idea of the math behind PLS. Okay, let's introduce one more definition. Estimator total unbiased station equal to the real value. That's to calculate. Okay, and after that, what we are doing is trying to like to guess what is this. Not guess, trying to get what is estimation of it. So what we are doing here is define difference between target variable and our estimation. Here it is. No, we like define from the estimation epsilon, as epsilon is equal to y minus x multiplied by w, and we like, and what we are wanting to do is try to find like optimal value for this, just using derivatives here. So yeah, and after some steps we can see that weight is equal to this thing. But it's important to say that, for example, here we see like that we use here inverse matrix, but in further we will also consider the case that this matrix could be not inversible. So yeah, and we set up these restrictions because we want to like follow the Gauss-Markov theorem, because it said that this solution will be efficient, optimal, and so on, so it will give us the lowest variance. Okay, so yeah, like I said, I haven't checked this, but I guess it's true. Okay, so yeah, I will not go further. I think I can stop right here. Yeah, well, I did some progress. I finished theory, but like I said, I didn't understand everything. So yeah, I will continue probably on Thursday, but so yeah, I will continue on Thursday, and there is very small probability that I will continue tomorrow, but today I don't know. But yeah, there are some things that I need to do, and if everything will be fine, I will not stream tomorrow. But anyways,